So everybody knows that speech is produced with your tongue. That's why language is called language, because we use our tongues to produce it. So here's a lateral X-ray of the tongue during the during production of the utterance. Why did Ken set a soggy net on top of his deck? You can see that the tongue tip is starting to move up toward the D. This is at the beginning of the utterance. This is an image of Ken Stevens that was taken by Stevens and Sven Ehrmans in 1962. They were doing a study of co-articulation. And for today, what we want to understand is just the basic division of the speech production mechanism into sort of two sections. The first section is this resonant cavity between the glottis and the lips. This resonant cavity we call the vocal tract. It's composed of, it's walled off by the tongue on the bottom side and the palate on the top side and the lips on the front, and in the back it includes the pharynx all the way down to the glottis. The glottis is a term that we use actually it's a Latin term for the hole between the vocal folds. So it's the empty space between the vocal folds, like the hole in the donut. The vocal folds are these flaps of tissue that close off across the top of the trachea. And the main purpose of the vocal folds from a survival point of view is that they close to protect your lungs when you eat. As you know, the pharynx branches into two tubes at the bottom of the pharynx. One tube goes to your stomach and one tube goes to your lungs. And when you eat, you want to close off the lungs so that you don't get food in your lungs. But of course, sometimes you also want to breathe, and so the vocal folds have to be able to open so that you can breathe. And if you have your vocal folds open and you almost close your tongue or your lips while breathing out, then you get an unvoiced fricative sound, something like a f or a th or a s or a sh. These are the unvoiced fricative sounds in English. And of course, that's not a big variety of speech sounds. So if we want more variety of speech sounds, then we want to be able to both voice and unvoice our speech sounds. And we can do this by loosely closing the vocal folds so that they're touching but not too hard pressed together, and then blowing air through the closed vocal folds. And this causes the vocal folds to flap like a flag in the wind. So they'll flap open and then flap closed again, and then flap open and then flap closed again. That period is about 10 milliseconds for an adult male, and it's maybe 5 or 6 milliseconds for an adult woman. And for a child, it varies between about 200 and 400 hertz, depending on the age and the size of the child. This is, by the way, this is the most reliable difference between male and female voices. The voice change during puberty of teenage boys is caused by a sudden rapid growth in the size of the vocal folds, which is much larger than the growth in the size of any other part of the body. So when you blow air through your closed vocal folds, they flap, and that produces sort of a periodic signal. And so in order to show you the way this periodic signal works, I'm going to show you some drawings of airflow through the glottis that were drawn by Gunnar Font and Johan Liljekrantz and Jiguang Lin in their paper in 1985. So these are all drawings that I've cut out from that paper. First of all, here's some drawings of airflow through the glottis, and you can see that the airflow is periodic. These are examples with periods between 8 and 10 milliseconds. So this is a model of a male vocal folds. And you can see that sometimes it's more sinusoidal and sometimes it cuts off more abruptly at the point of closure. So when the vocal folds flap shut, they cut off rather abruptly. And the excitation for speech actually is caused by the change in air pressure resulting from this change in airflow. So when the airflow is increasing rapidly into the vocal tract, then the air pressure just above the glottis rises. And when the airflow suddenly shuts off, that sudden cutting off of airflow causes a negative spike in air pressure just above the vocal folds. And that negative spike in air pressure just above the vocal folds is very effective for exciting the resonances of the vocal tract. So the entire vocal tract between the glottis and the lips rings, kind of like a bell or like a clarinet. And that ringing in the vocal tract is what we hear as speech. You can't produce speech by just moving your tongue around. You have to moving your tongue around just changes the resonant frequencies of that cavity. In order to hear the shape of your vocal tract, you have to excite it in some way, either by blowing turbulent air through the vocal tract or by exciting it by clapping your vocal folds together once every 5 to 10 milliseconds. So from a signal processing point of view, the model looks something like this. We basically have two different ways of exciting the vocal tract. Either we periodically clap the vocal folds together, producing a spike once every capital P samples, or we blow air through a constriction somewhere in the vocal tract, generating white noise, basically, turbulence. And at a simple model, we're going to get rid of this simple model pretty soon, but initially let's start with a very simple model where we have a binary control switch that switches between purely voiced or purely unvoiced excitation. And this is really the only nonlinear process in this signal model, because after you've chosen a particular kind of excitation, then you just filter that excitation through the resonances of the vocal tract. And we can model those resonances as a filter in order to produce the speech signal S of n. Right? So essentially, those impulses are convolved with an impulse response, h of n, producing the speech signal S of n. And since we have convolution in the time domain, that means that we have multiplication in the frequency domain. So S of e to the j omega is equal to h of e to the j omega times the excitation, e of e to the j omega. If we want to know what the spectrum of speech is, then we need to know something about the spectrum of the excitation signals and something about the spectrum of the filter. For unvoiced speech, the excitation signal is essentially white noise. White noise is a good model of turbulent excitation. So the magnitude squared, the periodogram of speech, is equal to the periodogram of the excitation multiplied by the magnitude squared of the filter. So the expected value of the speech spectrum, the speech is a random signal now, right? And the excitation is a random signal. But the filter is not random. The filter is deterministic. It's set by the way you shape your tongue. And so the expected value of the speech spectrum is equal to the expected excitation spectrum times the magnitude squared of the filter. But the expected value of a Gaussian white noise signal has a spectrum of 1. And so, in fact, the speech spectrum is noisy. The periodogram is noisy, but the power spectrum is just equal to the magnitude squared of the filter. And so if you could somehow average over several consecutive measurements of the periodogram, you can get a really good estimate, actually, of the Fourier transform of the filter active in the vocal tract. And this works really well. If you take the magnitude squared periodogram and average over several consecutive 10 millisecond periods, you get a really good estimate of the frequency response of your vocal tract. Voice speech is a little bit different. It's not random in the same way. In fact, it's excited by a periodic sequence of spikes. You've seen that the vocal fold excitation is not exactly a sequence of spikes, but the most effective part of the excitation is just a sequence of spikes, which we can model as an impulse train. A sequence of impulses, one every capital P samples. So now we're going to need to define the fundamental frequency to be omega naught is 2 pi over capital P. And we're going to need to deal with this using a discrete time Fourier series, which is kind of like a DFT, but we might want to calculate the DFT using a different number of samples. So we'll really treat this using a discrete time Fourier series. So if the excitation within one period is equal to 1 only at n equals 0, and it's equal to 0 everywhere else in that first period, then the Fourier series representation is just the sum over capital P different complex exponentials of e to the j omega naught nm, and the Fourier series coefficient is just 1 over capital P. All right, then if we take the Fourier transform of that, the Fourier transform of a complex exponential is just 2 pi times delta of omega minus m omega naught. And then we scale each of those by 1 over capital P. And we get a spectrum that looks like this. It's as a function of omega, we have a delta function of omega once every omega naught, once every pitch frequency. So omega naught corresponds to about 100 hertz for a male speaker and about 200 hertz for a female speaker. And you can see that we have critically here what maybe people who have not studied speech don't understand. We have really effective excitation not just at 100 hertz, but at every integer multiple of 100 hertz, at 100 hertz and 200 and 300 and 400 and 500 and 600 and so on. So the speech signal that you hear is h of e to the j omega times e of e to the j omega. And here's a picture of that. Again, this is from the paper A Four-Parameter Model of Glottal Flow by Lilienkrantz, Lind, and Font in 1985. You can see that the excitation here are all of the very fine ripples. So the axis across the bottom and across the top shows that the entire frequency scale here is 4 kilohertz. This is a model of a male speaker, so the pitch period is 100 hertz. So you can see that in the first 1 kilohertz, there are about 10 spikes, about 10 spikes representing the first 10 harmonics of the fundamental frequency, of the pitch frequency. And every 1 kilohertz, there are about 10 spikes. And those spikes are then multiplied by h of e to the j omega. The smooth curve shown on this plot is a plot of the log magnitude of h of e to the j omega. And so we add the log magnitude of h of e to the j omega, that smooth curve, gets added to the log magnitude of the excitation, which is this series of impulses, one impulse every 100 hertz. And so you get, in effect, you get a speech spectrum where you can, again, easily see the shape of the vocal tract. The smooth curve is not audible. It's not in the signal that you hear, but that curve with all of the pitch harmonics in it does certainly demonstrate that the smooth curve has a resonance at about 700 hertz, and it has another resonance at about 1200 hertz, and another resonance at about 2100 hertz. And that information communicates the kind of vowel. This vowel is something like an or an ah, right? And so you can, when you hear these formant frequencies, these resonant frequencies, you can hear what kind of speech is being spoken.